Good morning! I am going to talk about thermostress. A change in temperature can cause a material to change its dimensions. If the temperature increases, generally a material will expand, whereas if the temperature decreases, the material will experience contraction. Most traffic bridges and roads are designed with allowance to prevent buckling and to avoid thermostresses. It has been found from experiment that the deformation of a member having length L can be calculated using the formula alpha L delta T, where alpha is a property of the material and is referred to as the linear coefficient of thermal expansion. L is the original length of the member, and delta T is the algebraic change in temperature of the member. We will be having a simple example. So we have a steel bar, and it is constrained to just fit between two fixed supports. It has a length of 1 meter, and it has a cross-sectional area of 10 millimeters by 10 millimeters. And it is at a certain temperature of 30 degrees Celsius. So in support A, there is a downward force, and in support B, there is an upward force. So in this problem, we have to determine the average normal stress developed in the bar if the temperature is raised to 60 degrees Celsius. Since the temperature rises, the material will experience expansion, and there will be thermal displacement at the top support, and it is counteracted by the force F that would be required to push the bar back to its original position. So this is our bar AB, so that means that the deformation of the bar AB is equal to 0. We can have this relation: the deformation, which is equal to 0, is equal to the thermal deformation subtracted by the actual deformation. We know that the thermal deformation is alpha L delta T, and we just have to substitute it right in the equation. Alpha L delta T subtracted by PL over AE. Since we are trying to find the stress, we have to find out what is P. P is equal to, manipulating this equation, it is alpha, we have to cancel L, A, E, delta T. So for this bar, since it is a steel, we have this properties, that is our coefficient of linear expansion, and our elastic modulus, and this is only for steel. So substituting this to the formula, we have 12 times 10 to the negative 6 per Celsius degree, and our temperature, of course, our temperature is the final temperature subtracted by the initial one, so we have 60 degrees Celsius minus 30 degrees Celsius, multiplied by 200 times 10 to the third power, so we have to convert it to MPa. And of course, our cross-sectional area, so this is a square, so 10 millimeters. We have to square it. We can get the answer, 7,200 newtons. Is the answer. We now have the force, but what are we trying to find is the stress due to the temperature. So that is a compressive stress, is force over area, and we have solved the force already. So that is 7,200 newtons over the area, the cross-sectional area, which is 10 millimeters, and we have to square it. Then we can now have the answer, 72 megapascal. So that's it. Thank you so much for watching. I hope you have learned a lot about thermal stress.